This is Jacob Lawhon, informative speech number 2. Most people think of time as an absolute force moving forward at a steady, unchanging pace. 1 second is always 1 second. 1 hour here is 1 hour everywhere else in the universe. We live our lives believing that time is linear, that it flows the same way for everyone, everywhere. What if I told you that this isn't true? Time does not take the same way for everyone, everywhere. It stretches and bends depending on where you are and how fast you are moving. This concept is known as time dilation and is part of the fundamental nature of our universe. It has major implications in the future of space travel and surprisingly even in our daily lives, which is why I chose to extensively research about this topic. Rooted in Einstein's theory of relativity, time dilation reveals that time is not constant, but can be altered by gravity and velocity, affecting both scientific understanding and practical applications in modern technologies. Imagine this. It is the spring of 1905. A patent clerk named Albert Einstein steps onto a tram in Bern, Switzerland. On this particular ride, he has an idea that would change the course of modern physics forever. He asks himself, what if this tram car were moving at the speed of light? As he imagined speeding through the city at 186,000 miles per second, he realized something astonishing. If he were traveling at the speed of light, the hands of the clock would appear frozen in time. But for someone standing near the clock, time would pass as usual, and the hands would continue to tick normally. This simple yet profound thought experiment led Einstein into a groundbreaking conclusion. The faster you move through time, the slower you experience. The faster you move through space, the slower you experience time. Akash Pinshin, an electronic engineer at the University of Mumbai, explains it more simply, stating, a car traveling 40 miles per hour is 40 miles per hour relative to a stationary observer, but only 20 miles per hour relative to a car traveling adjacent to it 20 miles per hour. This poses a serious problem for Einstein, as this concept of relative velocity is incompatible with Maxwell's fundamental laws of the speed of light. To make sense of this strange contradiction of why time slows down, Einstein devised another thought experiment. Picture this, a man standing on the train platform. At the exact moment, 2 bolts of lightning strike, one in front of him and one behind. Since he is standing still, he sees both flashes of light at the same time. But now imagine somebody is speeding on a train moving near the speed of light. From the moving observer's perspective, things look different. Because he is rushing towards one bolt and away from another, the light of the closer strike reaches him first. The flashes that seemed simultaneous to the man on the platform are now out of sync for the man on the train. This posed a huge problem for the physics of the time. According to the laws of motion, the speed of light should appear different depending on movement, but Maxwell had already shown that the speed of light always moves at a constant speed, no matter who's measuring it. The only possible explanation is that time itself must be flexible. This means there is no absolute time. It is always relative to the observer. Einstein called this time dilation, one of the most groundbreaking claims in the history of physics. Einstein first introduced his theory of special relativity, which explained how time and space are affected by motion, and did not include acceleration. And as he expanded his ideas, Einstein made an even bigger discovery. Gravity itself is linked to time. He realized that, just like space, time could stretch and shrink depending on speed and gravity. In fact, he combined space and time into a single concept, the fabric of space-time, a 4-dimensional stage where everything in the universe occurs. At first glance, people were skeptical. Einstein's theory said that massive objects, like planets and stars, do not pull objects toward them via an invisible force. Rather, they curve the space-time around them through the 4th dimension, and objects move along these curves. Imagine a heavy stone placed on a trampoline. The fabric stretches, and other objects roll towards it. The warping of space-time also affects time itself. If an object is falling towards the ground, it moves faster the closer it gets, and, as we previously established, the faster something moves, the slower through time it passes. That means time runs slightly slower near the surface of the Earth in comparison to a higher orbit. This effect has been proven. Scientists have measured that atomic clocks tick at different rates at different heights. A more extreme example is with black holes. Andrew May, who holds a PhD in astrophysics from Manchester University, reports how NASA has considered what would happen if a clock were put into orbit 10 kilometers from a black hole having the same mass as the sun. Turns out that when viewed through a telescope from a safe distance, the clock would take around 1 hour and 10 minutes to show a difference of 1 hour. Einstein's ideas are not just abstract theories. They are scientifically proven concepts that have reshaped our world and understanding of reality. While these concepts are incredibly difficult to understand, they actually have real-world applications. According to Vasanshi Chahari, a professional data analyst at Sanchari College of Engineering, the speed of satellites around the Earth is around 10,000 kilometers per hour. It is about a thousandth of the speed of light. Even at this speed, satellites experience time dilation. If this effect is uncounted, then after a day, your location could be 8 kilometers away from your actual location, according to GPS. Scientists have to adjust their clocks so they stay synchronized with time on Earth. Looking ahead, time dilation will play a crucial role in space travel and colonization. As humanity looks beyond its own planet, future explorers could travel for what feels like a few years, only to return to Earth where centuries have passed. Understanding and mastering time dilation will be essential for interstellar travel and communication across vast distances in space. Time dilation poses significant challenges to our common sense understanding of time. It shows us that time is not a fixed, universal constant, but something that changes depending on speed and gravity. This phenomenon not only deepens our understanding of the universe, but also plays a crucial role in modern technology in the future of space exploration. Thank you.